Hello, my name is Christian, and I'll be going over today's tutorial with you. Today, we're going to be doing a tutorial on optimizing the direction of your 0-degree plies. Now, this is the first part of a 5-part workshop series, so be sure to go through each of these different parts just so you get an idea of how to perform a composite optimization with MSC Nastran. In this tutorial, this is going to be our goal. We are going to start off with this composite coupon here on the left. Currently, for this composite, we have our 0-degree plies running in this direction. We are going to perform an optimization where we try to find the best direction for the 0-degree plies. By the end of this tutorial, we find out that the best direction would be in this direction that I'm indicating here in the composite coupon. This direction will yield the most lightweight composite design for the load cases we're dealing with today. Now, why is it important to determine the optimal direction for the 0-degree plies? Here in the bottom, and I'm only considering one side of the composite, I've gone ahead and performed a ply number optimization, assuming that the 0-degree plies run in this direction. I find out that I need 24 plies to avoid a failure index greater than 1. Here on the right, if I were to optimize and find a better direction for the 0-degree plies, I find out that after the ply number optimization, I only need 3 plies. So you find that if you're dealing with a suboptimal direction for the 0-degree plies, you will need significantly more plies to handle the load. Whereas if you have gone and taken the time to optimize the 0-degree direction, you'll find that you'll actually need fewer plies when you optimize the direction of your 0-degree plies. So this is why this is the motivation we want to optimize the direction of the 0-degree plies. For this example, we'll be dealing with this very simple composite coupon. We are going to go ahead and fix this on one side, and on the other edge, we're going to apply 2 loads. One load is going to be a simple pull, and then the second load case is going to involve a transverse load. And it's worth mentioning right now, some of you may recognize that the optimal direction of the 0-degree plies is actually in this direction and not necessarily in this direction. And the reason we know it's this direction is because, one, we have one load that's pulling, so we want the plies to go in the direction of the load. And number 2, we're dealing with a transverse load where, again, the 0-degree plies in this direction will be very effective for that second load case, or actually for both load cases. The P-comp entry. This is what the P-comp entry looks at the very beginning of this procedure. At the very minimum, you should at least start off with 1 ply. So that's what we have here. We have 1 layer defined. The theta is defined as 0. The thickness is currently defined as 0.125 millimeters. You really don't need the second layer, but I purposely included it just in case you're dealing with a scenario where you have multiple layers. Here, again, be sure to start off with at least 1 layer where the theta is 0. One other comment, we're dealing with the symmetry option in the composite or the P-comp. So even though we've only defined layers 1 and 2 in the P-comp entry, Nastran internally will build an additional layer 3 and a layer 4 that are mirrors or symmetric to layers 1 and 2. The 2D elements are currently configured in the following way. For each element is going to point to this local coordinate system. Now, why is this important? This coordinate system currently has the x-axis pointing in the upward direction here on this page. The direction of the x-axis for this local coordinate system determines the direction of your 0-degree plies. The y direction determines the positive theta for each of your plies. And then if we were looking at this 3-dimensionally, if you had an x here and a y here, So X, Y, and Z. Your ply 1 would go here, ply 2, ply 3, ply 4, ply 5, 6, 7, 8, 9, and 10. So you would start from a negative Z to define ply 1, and you would go in the positive Z direction to increment your plies. So again, all of these elements are currently pointing to this local coordinate system where we've defined that this is going to be the direction for the 0 degree plies. If we look at the 2D elements, we see that in the 8th field, field 1, 2, 3, 4, 5, 6, 7, and 8, this is where we define the pointer to coordinate system 1. And you'll see that this one actually points to this entry, which has ID 1, which is a rectangular coordinate system that we define. So this option here, it's what's defining all of these pointers to this local coordinate system. Now, how are we going to set up the variable to perform this optimization? What we're going to do now, we're going to go to that first ply, which is this golden ply. We're going to take this theta, which is currently set to 0, and we're going to set it as a variable x1. We're going to let this theta rotate or change. Now, why is this important? Let's go here and let's draw that current coordinate system 1. Oh, this is going to be Z, and this here is going to be Y. So right now, this is our coordinate system 1, which has an ID of 1. This x-axis is currently defined in the 0 degree direction. If we let the theta change, and let's suppose that the theta is currently here, so this is 0 degrees. Let's suppose the theta goes to negative 60 at the end of the optimization. So negative 60 here, and then we'll draw a dotted line. So if the optimizer at the end of the optimization tells us that the better theta is negative 60, this is telling us that we should rotate the 0 degree ply negative 60 degrees to optimize the direction of the 0 degree ply. And then once we know this offset theta, if you will, all we need to do is go back to the coordinate system and rotate this coordinate system by that value. In this case, we've rotated the coordinate system 60 degrees. When we rotate the coordinate system, we then rotate or move the x-axis, which again defines the direction of the 0 degree plies. So that's what we're going to do. We're going to let the theta of ply 1 vary. Once we know this new theta, this theta is going to be used as an offset for the coordinate system. Here on this slide is the optimization problem statement. I always encourage everyone to sit down with a piece of paper, draft out what your variables are, draft out what your objective and your constraints are. This will make things a lot easier when you're configuring your problem statement in the software. So I've already gone ahead and discussed the variable. There's one adjustment described here that's worth mentioning here. The adjustment is as follows. We are going to take the bounds that are currently set between negative 90 degrees and positive 90 degrees, and we're going to offset them by 360 degrees. So here the lower bound is now going to be 270 degrees and the upper bound is going to be 450 degrees. You might be asking, why am I offsetting this by 360 degrees? This is why. If let's suppose that you start off with the negative 90 degrees during the optimization. If during the optimization the variable changes to 0 and tries to change to a positive value, you'll notice that the optimization actually becomes stuck at a value of 0. and that's not good. And here, let me give you another example. Here, let me draw a simple plot. The horizontal axis is going to be the design cycle, and the vertical axis is going to be theta. Here, let's suppose we start off at -90, and during the optimization, the theta is going to change, and then when it gets to 0, it's going to stop changing, and it's going to stay stuck there. But what we want it to do, we want the optimizer to go in the positive or negative space without any issue. That's what we want. But again, since the variable is taking on a value of 0, the optimizer will become stuck at 0. So that's something we want to avoid. And the way we avoid this is by offsetting the range by 360 degrees. You'll notice that when we're calculating the stiffness of the composite, we're actually using a trig function to define the composite. And you'll notice that when we supply this trig function, either -90 or 270, we're getting the same answers. So this is perfectly okay. And then instead of working with an initial value of 0, after we offset it, we are dealing with an initial value of 360. For the objective, this is what we want to do. We want to make this structure as stiff as possible. And the only thing we have to modify is the theta of ply 1. And remember that angles are variable. So the way we're going to maximize the stiffness is as follows. We're going to try and minimize what's called the compliance of the structure. Each load case is going to have its own compliance or stiffness. You could think of compliance as the inverse of stiffness. Instead of trying to maximize stiffness here, we're going to equivalently say we want to minimize the compliance. Now, if you're dealing with multiple subcases, you have an option of using either the average, which is AVG, or you have the option of using the max. So in this case, what I'm doing is I'm trying to minimize the maximum or worst case compliance of subcases 1 and 2. The compliances are going to be defined by these two responses, A1 and A2. So before I go ahead and jump into the tutorial, let me just leave my contact information here. As always, if you want additional training, if you have any questions, if you want to do more complex optimization, or not more complex, but new optimization with machine learning, you're more than welcome to contact me at this email address. If you want access to today's tools, you can also contact me for access at this email address. So let's go ahead and jump out of this presentation, and let's go ahead and start the tutorial. At the very beginning, I always personally like to start off with a clean downloads directory. I want to avoid any confusion with other files. I'll go ahead and open the user's guide, and I will navigate to the composite section. And then once I'm here, I'll click on the download link to download the starting bulk data file. This bulk data file is going to have the model for the composite coupons. So you'll notice that it's currently configured for a statics analysis with SOL 101. We have the two load cases here, subcases 1 and 2. We have the P-comp, which is currently configured to use a theta of 0 for layer 1. All of our 2D elements are currently pointing to local coordinate system 1. So I'm assuming you already have this file. Maybe you created this model in a separate tool. This is the starting point for this exercise. So if I go back to the web app, I'll click on the optimization link, and I'll upload that bulk data file. When I upload the bulk data file, I will get the option, or I will get a list of all the different settings I can set as a variable. I could set the stiffness values, or the modulus of elasticity for the orthotropic material. I can set those as variables, maybe the Poisson ratio, the density. There are a lot of values you can set as variables. But here I know that I want to set the angle. So I'll search for theta. I want to set the first angle of layer 1 as a design variable. Here I can configure the bounds, and if you recall, we're dealing with bounds that are between 270 and 450. The initial value, instead of dealing with 0, we're going to be dealing with an offset value of 360. So the initial value is not 0, it's going to be positive 360. And then I'm done with the variables, and now I'll move on to the objective. Today we'll be using an equation to define the objective. Here I'll go ahead and type in minimize the max of A1 and A2. Here you'll notice that I get an error message. This error message is indication that you will have a failed optimization. So here, if we read the error message, we get told that labels A1 and A2 are not created. In this next table, I'll search for the compliance response, and I'll click on the response twice. And now I have responses A1 and A2. If I go back to this equation, I no longer have an error. The status icon is blue, indicating that this expression, this set of bulk data entries, are okay to go. If I go to the exporter, I'll get a message that I'm not done yet. I still need to work on defining this problem statement. So if I click on jump to table, I get taken to this section. It's called step B, configure DR span for your equation objective. The reason this is necessary is because currently the equation objective, which is equal to R0, the optimizer does not know where response A1 is coming from. Is it coming from subcase 1 or subcase 2? But here I just use the pull down to say the response is coming from subcase 1. And for A2, the response is coming from subcase 2. And then if I go back to the exporter, you'll notice that the error goes away. I'm now ready to download this set of bulk data files and perform my optimization. So let's go ahead and click on download, and we will go ahead and extract the contents, and we'll go ahead and start MSC Nastran. And while that's happening, let me go ahead and configure the next slide to look at in a moment. So in a moment, we're going to get a new theta, which at this point is unknown. So I'll use a question mark here to mean unknown. We are going to have to update this current local coordinate system. If you recall, we'll have to go ahead and rotate this coordinate system. So we update the direction of the 0 degree plies. And like I said before, we don't know if the optimal direction is going to be in this direction or in this direction. We really don't know that at this point. So right now, I believe the optimization is happening. Let's go ahead and see what the window is. Okay, so here are the results of the optimization. One goal was to minimize the objective, and if we look at the objective plot, we'll see that the objective has in fact been minimized. If we look here at the message, we are told that we did converge. So this optimization so far appears to be successful. If we look at the plot of the normalized constraints, we see that we get values of NA. This means not available. Basically, there are no reported constraints for this optimization. And the reason is because we did not define constraints. This is an objective-only optimization. If we look at the design variables, this is what we see. We see that the initial value of the theta was 360. If we offset that back, we subtract 360, we get 0. So the original theta is 0. Here for the first design cycle, we see that we have a theta of 450, which is equivalent to positive 90. And then here at the very end, we get an equivalent, or rather an angle of negative 90 degrees, which is equivalent to 270 degrees. One thing you'll notice that these two solutions, theta equals positive 90 or 450, theta equals negative 90 or 270, you'll notice that it yields the same objective value. So one question right now is, does it make sense that we have two solutions for this example? If you recall, earlier we said that intuitively, we know that the best direction for the 0 degree plies are going to be in this direction. One of the reasons is because we are pulling the coupon in this direction, so it makes sense to align our 0 degree fibers in this direction. So now that we know that, let's look at our original 0 degree direction. The solution, or the optimizer, has told us that one solution would be 450 degrees, which is equivalent to positive 90 degrees. And then the optimizer swung back around and gave us another solution, which is 270 degrees, which is equivalent to negative 90 degrees. So at this point, you'll see that both of these solutions align the 0 degree ply in the horizontal direction. So this makes sense to us. So now that we know this, we now have to do the following. All of these different 2D elements are currently pointing to this local coordinate system. So now what we have to do is take this local coordinate system, which currently has the x-axis in this direction and the y-axis here. We need to rotate it 90 degrees. In this example, I'm rotating it 90 degrees. So our new x directions should be in this direction here. So I can either modify the local coordinate system, but you'll notice that the x-axis here aligns with the x-axis of the default or the global coordinate system that has an ID 0. So before all of these elements are using this coordinate system to define the 0 degree direction of the plies. What I'm going to do now, I'm going to update this. So all the 2D elements are going to be using this other default or global coordinate system. So by doing this, I will effectively ensure that the 0 degree direction is running horizontally as suggested by the optimizer. So the way to do this is by looking at field 8 of your 2D element. Field 8 of the C quad 4 element. We're going to take all those ones and we're going to make them all zeros, where 0 is the CID of that default or global coordinate system. So let's go ahead and jump out of the presentation and make that adjustment right now. We're going to copy the original file and we're going to rename it updated files. We're going to open that bulk data file. And here in this column, I'm simply going to select all the ones in field 8. And what I'm going to do is I'm going to replace all of these ones with 0. Today, I'm using Notepad++ to make the changes with the text editor. One of the reasons I like Notepad++ is because of this function. If I press and hold Control-Alt on the keyboard, I can now select characters vertically. This is why I was able to perform this change from 1 to 0 very quickly here on the screen. Typically, you can only select text horizontally, but again, with Notepad++, I can select text vertically, which is very convenient when you can perform these changes. Now, once you're done with the changes in this file, be sure to save the changes. One other option is you can import this file into your pre-post processor. You can make the change there, and then you can re-export your updated file. So as a last confirmation, let's go ahead and import this new model into the pre-post processor we have here available on this operating system. So we'll go ahead and import the original model, which is in directory 1 starting files, and then we're going to import the new file that is in 3 updated files directory. So let's go ahead and see where Patron is at. So on the right, I'll go ahead and import the newest model. And then here on the left, I'm going to go ahead and import the original model. And there, in a moment, you'll see a lot of arrows. A lot of arrows and markers are going to be displayed, which is going to look very cluttered with all the 2D elements. So I'm going to suppress all these black edges. So I'll go to display finite elements and I'll select edges and I'll click apply. And then I'll repeat the same operation, display finite elements, edges, and apply. And now let's go ahead and display the direction of the 0 degree ply. If I go to utilities, display, ply material orientation, and then let me make the arrows a little smaller. So I'm using a scale factor of 0.05. Here for material direction, I want to look at the direction of the ply 1, and then I'll select all the elements and click apply. If we look here, let me see if I can zoom in here. You'll notice that for each element, the plies are all going in the upward direction, if you will. Here on the right, let me repeat the process of going to utilities, display, and ply material orientation. Here, I'll shrink the size of the arrow. I only want to look at the direction of ply 1, which is the 0 degree ply, and then I'll select everything here on the screen and click apply. Now we zoom in here, we see that ply 1 is now running horizontally, whereas before it was running vertically. So this is confirmation that I've successfully updated the bulk data file to use this new optimal direction for the 0 degree ply. Here, one last comment on Patron. If you ever want to remove the arrows, you just click on reset graphics and zoom out, and the arrows have been removed, and then click apply again to re-display the arrows. And again, you repeat the process. Reset graphics, zoom out, and so on and so on. Alternatively, you can click on the broomstick here, or this brush. So you can either, I think maybe it's not a broomstick, maybe it's a paintbrush. Let me go ahead and click on those icons, and I guess that didn't work. So remember, always click on reset graphics here and zoom out to see, to remove the arrows. So I think if I step out of here and go back to the presentation, I think we're pretty much done with this tutorial. I think you've seen that we have been able to successfully determine a better 0 degree direction for the 0 degree ply. Remember that this is very important, because if you do not pick an optimal direction, you're going to need more plies to carry your load. But if you are able to determine an optimal 0 degree direction, you'll be able to use fewer plies and you'll be able to produce a more lightweight composite design. So that's the end of this tutorial. Here, I'll go ahead and end off with my contact information here. As always, if you have any questions or requests, you're more than welcome to contact me. And with that, thank you so much.